Hi. Uh, Sorry, I am very late. So I think I am 8 minutes late. Sorry about that. So this is Somnath here, and I'm going to talk about the Mossbauer and CBT spectroscopy. So are you guys not able to hear us? Let me share my screen. Okay. So today we are actually talking about CD and CD spectroscopy. Basically, this is the introduction week. So we are talking about the CD spectroscopy. CD spectroscopy is a short name, that is the circular dichroism spectroscopy. So over here you can find this is the one CD spectroscopy, the instrumentation, how this is happening, and the right side is that the uh, the actual spectroscopy looks like. This is a 3D spectra of a particular protein chain. This is that will come into later part. So in the CD spectroscopy, there is a one major thing is that, so that is CD is active. CD is a spectroscopy. Where the CD spectroscopy, now question is the where the CD spectroscopy should active. The CD spectroscopy is generally active. The molecules absorb the light, and also that molecule should be chiral. That is the major fundamental things about the CD spectroscopy. So you all of you, we are all chemists, so we actually aware about this chirality, all those things. Now recoiling this chirality kind of things, in this first week professors also did this recoiling of the all those symmetry elements, symmetricity, chirality, all those things into the lecture. Now I'm also following up those in this live session. If you guys, some of you guys have some problem and issues regarding understanding anything, please let me know. i'll I will try to solve it instantaneously, otherwise in the next live session I will try to solve it. So now this is the city spec. Now coming to the main topic, this is how the city spectroscopy looks like. And the major factor is that CD spectroscopy, where your molecule should be chiral, and then that should absorb the light in the region where we are measuring. Now coming to the another factor, that is called as a chirality or symmetricity. Symmetricity is a very beautiful term in the nature. You will find everywhere the symmetricity. Let's suppose we have the banana leaves. Everybody, I think everybody knows the banana leaves. There is a middle portion of the banana leaves. You will find the all the or left hand side and right hand side are similar looks like, but there is another issue, they are not superimposable. Where the comes the superimpossibility in between two systems, that is called the chirality coming into the picture. Here the symmetricity in the nature, we find three types of symmetricity. Professor also talked about those things. One is the bilateral symmetricity, another is the radial symmetricity, another is the spherical symmetricity. In the bilateral symmetricity, there should be a one particular line or plane where you will find uh, the both side, one side have a similar kind of uh, things, another kind also have the similar kind of other parts. So let's here this this butterfly, we have one particular line over here, and there is a two parts of this butterfly line. That is, one part is that similar to the another part. If we pass through a mirror in between this, in top of this line, we'll definitely get the what is called a bilateral symmetry. There is a radial symmetricity. There is another option is the radial symmetricity. So here, let's this star face kind of. This is now ordinators. There is a this one is showing where we have a one center over here. This is the center, and then it's starting the. There will be a multiple section. We can divide it, and we get the similar symmetric systems. The spherical one. This is the spherical one. Symmetry. Spherical one always a symmetry. All of you know. So another thing. Let's talk about our hand. Our hand is something like my hand has a one problem. So our hand, both our hand are looks like similar, but they are not superimposable. Let's suppose we are showing this way. These are the both side are looks like similar, and it's something like divided by a mirror, and but they are not superimposable. This is not the superimposable. So here comes the chirality term. So our hand is mirror image to each other, but they are not superimposable. That means our hand is chiral. And there's some other molecule also there. They are chiral in nature. They have, see, one molecule chiral in nature. They have their own mirror image. They are not superimposable. So that's when that molecule are chiral. So now let's talk about one chiral molecule, that is, let's think about one carbon over here. There will be a defined group. Let's suppose CH3 over here and OH over here, and there will be some other group over here. This is, let's suppose, ET group over here, and then we have beer. Okay, let's suppose this is our molecule. This center is that we are calling it a chiral center. This center is the chiral center. So it suppose has its own mirror image. We are taking its mirror image. Okay, and then it should looks like carbon, and here is CH3. There will be OH. Here is the bromine, and sorry, I just need to erase these things. Yes, this will be my ET group, and this will be my backwards is the bromine. So this one, these two are mirror image to each other, but they are not superimposable. If you take this molecule, we took this molecule and try to fit it on top of the this one, on top of this one, will not able to fit it on top of this. Let's suppose this is called A, this is called B. We cannot fit it. So this is small, as this molecule is chiral, we cannot fit it. It has its own mirror image that is not superimposable to each other. This is called enantiomers. Enantiomers. And this enantiomers has a some physical property. So, both of molecules are enantiomer to each other. We cannot distinguish this molecule in our normal systems until and unless we put those molecules into a chiral environment. These enantiomers, has a similar physical property. Let's suppose it has a boiling point, melting point, freezing point. Everything are the same. Order will be the same. Everything looks like a similar. But when you will put into a chiral environment, they will behave in a different way. Let's suppose in our body there is a lots of amino acids. There is a lysine, all similar, like generally most of them the L protein, L amino acids. If we take the R amino acid, our body will not consume that. Some of drugs molecules are also present. Their one isomers are active for our body and also good for our body, and another form is the not active, or sometimes they are very bad effect in our body. So why happening so because of the our body is a chiral environment. Our body can recognize that this chiral molecule in a different way. Let's suppose our body recognize A molecules in a certain way. Now they can recognize the B molecule in a different way. So in the if we put this chiral molecule in a different chiral environment, they will show a different property, and therefore we can distinguish those molecules in a different that these are the different molecules. So in our nature actually made different kind of this. Nature is actually chiral. They make different kind of isomers and isomers. Those are biologically active. Now this is the chirality. This chirality terms associated with the symmetricity of the molecules. Now this symmetricity also associate with some quantum mechanical term that is now coming as symmetricity. This is asymmetric molecule. Asymmetric molecules. Okay. This isomers, this bromo alcohol is the asymmetric molecule. So it's associated with some term that is called symmetricity, symmetry of a system. Sorry. Okay. Symmetry. Symmetry. Okay. Okay. Now come to the next page. Symmetricity. The symmetricity is associated with some quantum mechanical. QM is the quantum mechanical term that is called Schrodinger equation. That is H psi equals to E psi, where the psi is the wave function, wave function of electron. and E equals to energy, and H is the Hamiltonian operator. Okay, so this is this is the operator. There should be operator sign, and then this represent the psi. This psi actually represents the electron movement, the movement of the of electron, and H actually the decides the it actually controls this movement of the electron. H controls the movement of electron. It contains different kind of parameters that actually control where the my electron should be, where my system should be, and that elements actually besides the all kind of parameters, or symmetric parameters, or all those things actually contain the symmetry parameter. One term is that symmetry parameter. Okay, so and then this E actually show the energy depending on the energy we can distinguish or indistinguish my system. If say energy is similar, then it becomes the degenerated system. Same energy becomes the degenerated system. Okay, now now we can easily we can easily say this this Hamiltonian system that contains our symmetry element. If that if we control the function wave function of that electrons, that means molecules or any other thing, and we find the same energy, there should be a indistinguishable, both the elements, the system is indistinguishable. So in that case, if two of them are energy same, then it becomes the degenerated system. So how we can say that one kind of degenerated system we have? Let's suppose benzene molecule, all the hydrogen over here, hydrogen, 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 and this hydrogen. Okay, all of hydrogen. If we put the Hamiltonian operator for those system, so overall there will be a sum. Let's suppose benzene psi v. If we put onto the Hamiltonian operator, H psi v psi dash b equals to EB, sorry, psi 1 1 1 psi dash E 1. So So the energy should be this B1. If B1, B2, B3 are similar, for this benzene molecule, we have EB1 equals to EB2 equals to EB3, and so on and so forth. For those, this hydrogen 1, hydrogen 2, hydrogen 3, hydrogen 4, 5, and 6. So it becomes non-degenerated system. This is the degenerated system. That means all of them, for those all of them, we have the one particular energy value. And for the supporting for this, we have the 1H NMR spectra. It shows only one signal in NMR. So because of they are all those hydrogen proton molecules, protons are not protons are degenerated, and the energy are similar. In the spectroscopy level, they found the same kind of energy in the these all six protons. Okay, so this is a one kind of symmetric molecule. Okay, this is a symmetric molecule. Now coming to the now another definition of what, so this is a one kind of mutual relation of the ports of an object in respect to magnitude, portion, or relative measurement and arrangement of part of a system. Okay, this actually this definition has been found in the Oxford Dictionary system, Oxford Dictionary, and this is the mutual relation of a on particular person. Let's suppose we have the benzene molecules. Do we have the one particular? Let's suppose all the protons. If we took into the NMR spectra, we'll getting the uh, getting one particular spectra because of the all protons are relatively related to other proton, and it's similar to other proton. So this is the one kind of relation that all the protons are in same. Okay. Now we have some other molecules. Let's talk about the other molecules. We have this is a layer in case of benzene. We have benzene, or it is a highly symmetric, and then we have another molecule. Let's suppose we have some X group over here. Let's suppose my CH3 group over here. This is the called toluene. Toluene, it has, let's talk about how this is a proton, this is a proton, this is proton, and there is another proton. So this one, two, three, this will be two, and this one will be one. Because of this, both side of this are similar. This is the metaproton, this one also metaproton. It looks similar. This one also paraproton. So here three NMR signal will get 31H NMR for aromatic proton, and one H one signal NMR for CH3 group. So because of this proton, this orthoproton, this metaproton and paraproton, they are different in energy. So this is less. So that's why we'll getting the less symmetric system. Less symmetric. So our other example is there is another molecules. Let's suppose we are substituting another group. Let's suppose we have two CH3 group over here, CH3. We have this is this is the molecule substituted, para substituted one. It will also have one particular NMR signal, that is one NMR signal. It also have one particular NMR signal for aromatic proton. Okay, because of it's also a very symmetric molecule. It's a very symmetric molecule. How it becomes more symmetric, I'll come into later on. Okay, then there is another molecules. Let's talk about the ortho substituted, orthomethyl substituted toluene, that is CH3 over here and CH3 over here. So here in this case, hydrogen, here hydrogen. Sorry about my drawing. Very, I am not satisfied with it. So it also has, so how many protons we have? We have, this one will be the same. Sorry. Uh, and this proton, and this proton will be the similar looks like, and it will have the two NMR signal for aromatic proton and one NMR signal for aliphatic. Okay, now coming to the next. So why this is happening? So what symmetric? Why we are saying that this is the less symmetric? This is the more symmetric. So there's some mathematical operation that is called the symmetry operation, and that is associated with the some symmetry elements. So now coming to the some symmetric operation. This is the symmetric operation called symmetric symmetry operation, and symmetry elements. These are the major terms that will come into picture in the also next couple of classes in the NPTEL also, and also I am also majorly discussing about this in this class. Okay, so we are talking about that Hamiltonian operator, right? This Hamiltonian operator actually associated with the operation. This is the let's in case of the symmetry operation. This is actually doing this symmetry operation, which is actually another kind of movement, such that it offers movement has been every point the molecules coincides when we can say some molecules it's the sorry about that uh, symmetry operation, a movement such that after the movement has been exhausted every point of the molecules coincide to an equivalent point of the molecule in the original position. How? Let's talk about the circle. One circle over here. If we bisect over here, we'll getting some. Not this one. Sorry about that. We have a circle, and there is a point over here. This is a point. With that point, with respect to that point, if we rotate on top of this axis by x degree, x can be near to 0, near near to 0, then we can some little movement, it did not change its, it looks like it doesn't change its actual position. So that means they are actually looks like a similar at the similar position. So if we rotate, it will superimpose to on itself only. So that means it is a very symmetric system. Symmetric system. And this is the symmetry, this is this rotation, this whatever we are doing, this we are talking about the rotation. This rotation is called symmetry operation. This is the operation kind of thing. And the the axis on top of that axis which is called the symmetry element. With respect to that axis we actually did the rotation, so this is called symmetry element. Okay, so there's some different symmetry elements are present. With respect to it, that symmetry elements are symmetry operation. With respect to the symmetry operation, we actually divided all those symmetry elements into five five different elements are present, and five different operation we'll get. Now coming to the first one, this is number one. Let's talk about the symmetry operation, that is called the rotational axis of symmetry. Rotational axis of symmetry. This is called Cn. For the n equals to 360 degree divided by theta, and the theta equals to the amount of rotation, the amount of rotation requires to make superimposable mirror image. Okay, and that's maybe this n may be 1 2 3 4 infinity. Now coming to one example, let's talk about tribromobenzene. Tribromobenzene, we have benzene molecule. Here is the bromine, here is the bromine, here is the bromine. Okay, now what kind of operation we can do to make a superimposable of its structure? Right now we are talking about the rotational axis. How much degree of rotation we need to make its superimposable mirror image? Not mirror image, superimposable of its structure. If we rotate, there is a point. This is the point. Let's suppose this is the point. This is the point. With respect to this point, with respect to this point, not like this. With respect to this point, we have a above the plane and below the plane axis. This is the axis of the plane axis. If we rotate 120 degree, we'll again this, let's suppose name is this is BR1, BR2, BR2 and BR3. So if we rotate it 120 degree, we'll get this uh, very this one is that. Now if we are rotating, so this will be the BR2, and this will become the BR1, and this will be the BR3. So but we actually mark this as a BR1, BR2, BR3, but in general case it's not. So so it becomes looks similar. it, if we take it into and superimpose into that initial molecule, it will fit. There is no point will be not fitting. So that becomes this this is becomes super possible, super impossible. So, and then this rotation is called, this rotation this rotation axis is called the same element. This is the axis element, which is actually axis of rotation, which is named as the C3. 3 comes from 360 degree, and whatever we rotate, that is the 120 degree, so equals to 3. So this is the rotational axis. We have these molecules. This is the major axis. We have the some other axis also be there. So let's there is a there is a another axis over here. If we rotate it with respect to this will be the 180 degree rotation. There will be the another over here. There will be the another over here. So all those are the rotation with respect to 180 degree. So these are the C2. So this molecule with respect to rotation, this molecule having the C3 and 3 C2 and 3C2, and then this is a this is 3C2, and then this will be the my molecule. Which one will be the major axis we are talking about? The C3. The minimum disturbance needs to make a another similar kind of molecules. If it is generate minimum amount of disturbance, this is the C3. 120 degree rotation is the minimum disturbance over here. Makes the similar molecules. So this is the C3 will be the major rotational axis. Okay, now coming to the some other example. So some other example, let's suppose now we need to find out how many uh, let's suppose ethylene molecule C double one C proton proton. How many rotational axis? Rotational axis. So this is a molecules, but this we have to after the rotation we have to make a same molecule. So let's freshly write over here C double one C. Here is the proton, another is the proton. Here will be another proton. Okay, so there is one axis with respect to this one. If we rotate with respect to it, we will get the same molecule C double one C, hydrogen, nitrogen, hydrogen. So 180 degree rotation, and there will be another over here. If we rotate over here 180 degree, this will also again make this same molecule. So this is called C2 operation, this one also C2 operation. So it has the two C2 with the rotational axis. It has two rotational axis. It also has some other elements we'll come into later on. Okay. Now coming back to another second number of elements, that is rotational through a plane of symmetry. Okay, this is a rotational. We are doing the rotational. This is the element. Rotational is the element. Rotational operation. Oh, sorry, rotational is not the rotational is the operation, and the element is the plane element. This name as the sigma. Okay, and then one example is that again we are taking this tribromobenzene. We have the tribromobenzene over here. Br, Br, and this is the Br. It has a. This is the molecule. Later on, we'll come into tribromobenzene. Now we'll take another example. This is a different example we are taking. We have the one particular molecule. This is called the water molecule. Let's suppose talking about the water molecule. Initially, let's talk about water molecule. This is H, and then we have this is the rotational axis. We have this is the C2, and with respect to this C2, there will be another mirror image over here. If we bisect this water molecule, both sides of our will be similar. So it has a one sigma phi sigma v over here. Another sigma is the plane of this water molecule. This is the plane of the water molecule. There will be the another sigma v. Sigma v. V means vertical. V equals to vertical, and the vertical because of the uh, it is parallel or contains the principal rotational axis. Rotational axis. Now coming to the another example, we have the now coming to the that example, that is that tribromobenzene. So now question is the how many question is the how many sigma v present, and another term is the sigma h present. So our principal axis is over here, and then go beyond the plane of my paper, my screen. So this is the my rotational axis with the C3 axis. We have the sigma plane. Where we have the sigma plane, there is a one sigma plane over here. Sorry, this is the sigma plane, another sigma plane over here. Bisecting this molecule, there is another sigma plane. This is bromine on this point. So we have the three sigma v because of contains the this sigma v contains the my principal axis of symmetry. And another is that with respect to this, the plane of the molecule, let's suppose our screen, plane of the screen, this is the sigma h. So this molecule have sigma h, this is the horizontal, this is the plane of symmetry, plane of symmetry, symmetry perpendicular to the principal axis of rotation. Rotation. Okay. So this molecule have, so it has symmetry element with respect to the plane of symmetry present. Symmetry is it 1 3 sigma v and 1 sigma h. There is another interesting thing. Let's talk about the nickel tetrachloride. Nickel 2 tetrachloride. This is the nickel structure is the square planar. This is the Cl, nickel 2 plus Cl, Cl, and then Cl. We have a negative charge 2 minus over here. Nickel 2 tetrachloride, it has the symmetry element. Let's find out the symmetry. The what is that? Plane of symmetry. How many plane of symmetry? Number of plane of symmetry. Okay, so one is thing. This is the principal axis. It has the C4 over here. This is the below the line and the above the plane. Above the plane, this line. This is the below the this screen. This is the axis. We have the C4. Oh, with here we have C4. That means this is the principal axis. So how many we have? How many planes which is actually bisecting these molecules and make a similar point with respect to this plane. So we have one plane over here, one plane over here, two sigma plane, two sigma v plane, which is actually bisecting this two chlorine molecule, two chlorine atom. More interestingly, there is another sigma plane over here and there also. So plus another two sigma v. sigma v equals to total num 4 sigma v, and there is a another another there is another is that another plane over here. This is the sigma h plane of the screen. That is the sigma h 1, sigma h also be there. So total symmetry element, mm, sorry, this sigma h, and we have 4 sigma v and 1 sigma h, and more interestingly this sigma v contains the onto the it is that it is that contains on top of the principal axis of C4, so it calls as a sigma d. Okay, so we have principal axis on top of over here. It contains the 4 sigma v, and it bisecting the 2 C2 perpendicular to the, we have the 4 C2 with respect to here and 4 plane also there, so that's why it is called the sigma d bisecting. Now another term is the reflection to a through a center of symmetry. 3 is the reflection center of symmetry, that is called as n. So this is a combination of two to previously discussed operation. One is that it is a rotation. Second thing is the reflection. So example, let's talk about, and this n should be, oh sorry, this is the what I said. Oh sorry. So this is the reflection through a center of symmetry. This is the I. I did this mistake. Sorry. Should be I. This is called I. And this is another name is center of inversion. So that's why it is called I. Center of inversion. or I. Okay, some molecule. Let's suppose we have a one molecule. Now can take a one molecule. Sorry, it is benzene. Our easy example is the benzene. Proton, proton, proton. If we center of inversion, there is a one point particular point. This point is called center of inversion. So we have if we go through this point, after this point, again we will find the same system similar to this to this. So this is the point we meet. This point is called center of inversion. Another example is that my CO2 molecule, hydrogen molecule, sorry, hydrogen should be single. This is the hydrogen molecule. We have the center of inversion over here. This is the I. Here is the I. Same to let's talk about the another molecule is a defined molecule. Let's talk about the nitro NO. NO looks like here N double bond of triple bond oxygen and plus minus sorry, something like this. Nothing. Or we can not going into the debate. So how it should be, should be plus or which one will be the thing. We don't talk about this debate. This is the carbon and carbon monoxide. Let's talk about the carbon monoxide. We have this is the carbon monoxide. If we think about here is the I. This is not on top of this point. This is the carbon. This is the oxygen. So there is no I. So it doesn't contain any I. So this is not possible. Next, another molecule. This is the nickel we previously discussed. The nickel tetrachloride, nickel 2 tetrachloride Cl, nickel Cl, Cl, and Cl 2 minus. It also has one center center of the symmetry. This nickel say nickel in this point. There is a one I over here. Similarly, some hexacoordinate complex. Let's suppose cobalt hexachloro cobalt hexachloride anhydrous. This is 3 minus. Okay, so it is a octahedral, the octahedral complex. This is the square planar, sp square planar. It's the octahedral complex. Its structure is looks like my cobalt center over here. Here is with a Cl. Ah, here we can easily write the flying wedge conformation. This will be the below the plane CL. This will be the above the plane CL. This one also above the plane CL, and this one will be again CL, and this is the on the plane. So it also, if we go to from this side, start, and then in this point, after this point again we start going, there will be same environment over here, and similar to this side and this side also. So in this cobalt center, the I also, there cobalt hexachloride, hexachloro cobalt 3, it also has center of symmetry. Similarly, we have some other molecule similar structure is that SF6 xenon, sorry, xenon, xenon XCF4. This also has a similar structure of this nickel chrome system. All those system has a center of symmetry. Okay. Now another symmetry element. This is called, or is the improper axis of symmetry. Axis of symmetry, which is named as the SN. So this is consist of two particular operation. One operation is the rotation operation. Cn. Again we have sigma h reflection around a plane, reflection around a plane, which is actually perpendicular to the Cn, and this n we know, n equals to 360 y theta, previously as we know. So now coming to the another discussion, let's take another example. Okay, we have the some complex nickel carbonyl complex. This is the NiCO whole 4. Nickel is in zero state, nickel 0 for carbon. It's a tetrahedral structure, tetrahedral geometry. So we have, this is a nickel, and we're drawing something different. Oh, this is my CO, this is my CO, this is the one plane, this is CO, we have this thing of CO. If we rotate, let's suppose there is a axis, this is the axis we are thinking about. If we rotate 90 degree, how it should looks like. This carbonyl will come above the plane. So that means we have nickel over here, and this will be my C. Bad with my writing. Sorry about that. This one is a CO, and this carbonyl will go back. This will be the CO, and this carbon will this side come becomes a CO here, and this carbonyl goes to that side in that plane, and it becomes a CO. Now, if we take and superimpose onto this, it will never superimpose on this in my initial A structure. Now we get the B structure. Now we are taking a reflection. Let's talk about from here. We are taking a reflection. Okay, and then we'll get this is the nickel. This carbon go to this side. This one will be go to this side, and this will come back again below the plane. This is the CO. This is CO. This one is CO, and this one is the CO. You will take superimpose onto this, you will get the similar structure. So this molecule, one more interesting point, it doesn't contain this molecule. This is doesn't have individual just a minute. This molecule C4 don't have. We have sigma don't have, but it contains S4. It is a combination of C4 mm, sigma H. Okay, so this is the beautiful operation. The molecule don't having the C4 axis or any principal axis of symmetry, and as well as the sigma, but it still contains C4 axis. But this is the tetrahedral molecule. It don't have the C4 axis and also sigma H, but combination of those actually having making another symmetry elements. It is the S4 improper axis of symmetry. It combination of these actually have some symmetry showing the some same superimposable structure. So that means this is another beautiful things. This let's talk about another. We let's talk about the system having the rotational axis is C1 and having one sigma H plane. It becomes it's called sigma H. Why? Because of this is called the sigma, not the sigma. It will call the sigma. Molecules having C1 rotational axis and in the sigma H plane, it is this symmetry operation is called the sigma. Similarly, molecules having C2 with its sigma h, it is called the I. It is we can find it in a different symmetric book, that is some kind of group theory book. All those things we'll get this, how this C2 and sigma h combination make I. Okay, there is another element which is called identity operation. Part number 5 is the identity operation. So whenever we have some molecule only have the C1 axis, that is the rotational axis only C1. This is called the E rotation rotation only for 360 degree, sorry, 360 degree rotation. Only 360 degree rotation. This is called E. E means NH. This is a German word. This is HEIT. NH. This is German word. So this is the nothing but we have some system where rotation is 360 degree. That means we are doing nothing. So let's suppose we have a circle. We start from a one particular point and came back again in a starting point. This is kind of same kind of thing. This is a 360 degree rotation means we have some system where we start one 360 rotation and again come back to its initial position. So this is called the identity operation operator. Okay, so in the mathematical term, we have total number of mathematical operation. So mathematical cal, what are the operation we find over here is the 5, that is Cn sigma center of symmetry, and we have the improper axis of symmetry S4, sorry, Sn, and followed by my what is that it's an identity element. These 5 elements actually present in the all those symmetry operation. Okay, so now having into this all those symmetry element, the molecules can be divided into some groups, that is called as symmetry division or by point groups. The sorry molecules can be divided with respect to presence of all those element in that molecule. With respect to it, uh, we can divide those molecules in a particular groups, that is called symmetry division by point group. Within it we have three different things. not the three. This is the four. Four different group we have. One is called non-rotational group. Non-rotational group. Second thing is that single axis group. Third is that dihedral group. Four is the cubic cubic group. Okay, so we'll get some examples in our upcoming live sessions. Now the time being, what are the symmetry elements presence? There is some division over here also, and each particular groups, and what are the symmetry elements actually present in that group. We are going to discuss it right now. So now coming to the first one is the non-rotational group. Non-rotational group. It actually divided into three parts. One is the CN, CN constants element only E. This is the elements, and this is the group. Second one is the it has the CS. It contains only the identity operator and the sigma. Third is that CI. It's having the identity operator and the center of symmetry. These three called non-rotational axis group. Non-rotational. It doesn't have any rotation. Doesn't have any rotational axis. We second one is the single axis of single axis group. Sorry. Second one is the single axis group. It also divided into four parts. Four, no, not four. This is the five parts. It also has one. One is called CN. Sorry, C1. This is the C1. CN. It contains the identity operator, followed by it has CN, CN2, CN3, up to Cn n minus 1. Second is that it's having CNV point group. CNV point group. We'll discuss about the example in the upcoming live session, which having the it also have the identity operator Cn Cn n n minus 1 followed by n number of sigma phi plane. Third is the third is CNH. We have CNV, we should have the CNH. That is, we have the E, Cn, Cn n minus 1 and followed by sigma H. This is not the n number of sigma H. In case of CNV, there should be n number of sigma V. Now another is that 4 is 4 is S2n point group. S2n point group. It contains what it contains. This is the E identity operator Cn 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 n minus 1 followed by sorry this will be the Asn S2n. I'm sorry about that, guys, because of some mistake. Uh, screen has been screen share has been stopped. Just a minute, I'm doing it once again. Okay, I think it's again visible. Okay, where I was here, making it full screen. We have S2n S2n over here to S2n n 2n minus 1. Why it is so will come into later on when we are discussing individual part, because of this number should be even number. Now another is the C infinity phi, so it should contains identity operator, C infinity axis, C infinity C, and also it should contains infinity number of sigma v. So infinity number of sigma v. So it is a linear molecule. Let's talk about some linear molecule over here. Some linear molecule. We have the linear molecule. Let's suppose hydrogen or other thing. We have a sigma. This is the axis, or we can get the this is the C infinity, and that this is the point over here. We can make lots of axis, sigma v axis. So this is called the. Hi Sarthok, are you hear me? Okay, this is actually period of time between 7 to 9. So you are too late. Do you have any doubts regarding all those things? Okay. Do you have any doubts regarding if you want to stay, then stay. Just I am wrapping up. Okay. So I think you covered with that lecture part. If you have some questions, yes, go ahead. Go ahead. This is the classification. So we have some four different kind of classified, majorly classified point groups. Within it, there is a some subgroup also be there. Let's suppose C1, CS, CI. See here, you can see the C1, CS, and CI. What those, what kind of groups it is, what kind of elements should be there in that point group. That is the measure we are looking for. So we are actually making some division of the group, so we can easily we think about that. This is the molecule, it has this kind of elements. Let's suppose we have some CNV kind of molecules, CNV point groups. In there are some molecules, it's supposed to have one identity operator that should be 1 360-degree rotation. Then there should be some uh, rotational axis, n number of rotational axis, and n number of sigma v. So with respect to that, we are actually making it, wrapping up all those things that in together. So we have this much of elements, so that should be, my molecule should be in that point group. That is the main focus of our discussion over here. Okay, do you have any other? Okay, and then any other questions? If you have any doubts regarding the your tutorial, that is the tutorial, that means tutorial question answer, we can only solve after your tutorial has been submitted. Because of we tutorial is open right now. If I solve it right now, you can make a, you can, somebody can change their answer. Okay. If you have any doubts regarding okay. So this is, we are actually talking about at that time I was actually talking about how C infinity if should looks like. So it should have some uh, elements, that is the identity element. It should have uh, C infinity axis. That means we have one rotational axis where my rotation should be minimum. That means near to the zero, and that in that point group there should be some infinite number of sigma v flame. So now coming to the one example is that this is the my hydrogen molecule. Let's suppose hydrogen molecule. So this hydrogen molecule, it has a, this is the axis is the C infinity. This axis is the C infinity axis, and with respect to this point, we can uh, sorry, we have a some, array, sorry, we have infinity number of sigma v plane over here. In a minimum distance, we can infinity number of sigma v plane. So with respect to that, we can say this will be the one molecule having the point group of C infinity V. This hydrogen molecule is the C infinity V under the C infinity V point group. So now coming to the another point group, that is major point group, is that this is the dihedral groups. So in the dihedral groups, that is denoted as Dn. That should be capital D, and small d should be defined denotation. So we supposed to use the capital D. Just a minute. Okay. So it also divided into some other parts. That is, one is called Dn. Another is that DND. DND. Third is the DNH. Four is the D infinity H. So what elements should contains in that point group? There should be identity operator. There should be Cn to Cn n minus 1, and there should be n number of C2, which should be perpendicular to the Cn axis. This is the criteria you have to match. Otherwise, this is that molecule is not under the Dn point group. Now coming to the DND point group. So it should have identity operator, as well as similar to the dn point group, it should have cn to cn minus, sorry, n minus 1 number of rotational axis, and then we'll have n number of c2, which is perpendicular to the cn axis, followed by s2n, followed by there should be s2n and 2s2n 2n minus 1. Do you know why this is n minus 1? Yes. So let's suppose you have some molecules having square planar geometry. Okay. Let's suppose this is the your system, nickel, sorry, nickel, your chloride, 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 chloride. So you have this axis, principal axis. This is the C4 axis. Whenever first rotation you are doing, this cl becomes this one becomes this one becomes this one. As how you rotate third time, after third time, if you rotate it, this cl becomes comes to into in its position only. So that means you are rotating 360 degree. So that's why this we are not taking as a this one, because of the we have already identity operator. So this is nothing like a identity operator, so we are actually taking only n minus 1 numbers of rotation. Okay, good. And then this is the element we have we should have in dnd uh, point group. There is another dnh, which is actually contains identity operator. Every point group should have the identity operator, then followed by cn to cn minus 1, and followed by n number of c2, which is perpendicular to the cn axis, and n number of sigma h. Sorry, this is dn. Sorry, this will be the dn. This is dnv. Will it be dnv? Yes, yes. In number of sigma b, and last one is the d infinity h. Oh, sorry. This will be the element. It should have the c infinity to c infinity minus infinity minus 1. So it doesn't sense anything. So we don't know the infinity. So it's better to remove that one. And then we have the infinity number of c2, which is perpendicular to the c infinity axis, and then there should be some sigma h plane and infinity number of sigma v plane, and also it should contains center of inversion and also improper axis of symmetry. That much of element it should have. This is similar to the always that much of elements should contains in a linear molecule only. So similar to the hydrogen, this is a hydrogen molecule also fall into this point group. I just took initially that is that this is not the actual uh, C P C C infinity point group. This is actually hydrogen molecule is the DNH point group. Now another point group is present, that is the this is a cubic point group. This is the higher order, it has the higher order term. So this is cubic point group. So it contains one a tetrahedral point group. Second thing is the octahedral point group. It generally lots of symmetry elements. The total number of symmetry element is total numbers around 24, and for the octahedral it becomes 24, it becomes 48. So we have the list, but it's very difficult to find it. So generally some similar just like some tetrahedral molecules having a cubic kind of structure, not the tetrahedral structure. It's maybe fall into the tetrahedral point group until and unless it has the similar kind of ligand environment. And also for the octahedral, we have, let's suppose we have some uh, SF6 molecules. These molecules, sorry, uh, SF6, we have the cobalt hexachloride, cobalt 3 hexachloride, Cl6 whole 3 minus. This actually fall into this octahedral, and here also you can say nickel tetracarbonyl, this complex. This also fall into this tetrahedral point group, and this one actually fall into this octahedral point group. Okay, so I think it's time to finish it, wrapping up. Actually, we covered it today. Some introduction of the CD spectroscopy. So how actually CD spectroscopy looks like. This is the we actually talk about how the instrumentation actually happening. Now this is the in the left hand side. This is the how CD spectra looks like. This is the CD spectra of the some protein. That is the alpha helix helical protein. One is the beta chain protein. Another is the random coil protein. The black one is the random coil. Green one is the beta chain, and the alpha is the sorry alpha helix. Alpha is the alpha helix, and the beta seed will be the defined structure. That is the green one. So next we introduce why the symmetry is more important. The where the symmetry has been found. If you took into the some leaves like bay leaves. So bay leaves, if you divide it into middle of that mark, then you will get the similar kind of parts. It's kind of symmetric kind of things. So similarly, how three types of symmetry has been found in the nature. So with respect to that, bilateral, radial, and spherical symmetry. Now we actually introduce why the symmetricity comes into picture in our nature. Why requires the symmetricity? So that our body is chiral, so it could recognize one chiral molecule, and it becomes a it becomes recognized and becomes the diastereomers in our body, and then that molecule is actually consumed by our body. So, and with respect to it, we can actually isolate the isomers, one enantiomers from the another enantiomers, with providing these enantiomers into in exposure into the into a chiral environment. Then we talk about some symmetry elements, why the symmetry elements comes, why in how where the symmetry elements actually put into that. So here comes the Schrodinger equation, one quantum mechanical term, and with respect to that, we solve some NMR spectra, why this NMR spectra comes from, why this degeneracy comes into the picture, and then followed by some symmetry elements, coming to the symmetry and symmetry operation and symmetry elements, all those symmetry elements followed by groups, and finally we actually covered how many groups point group are present for the molecular systems. So with respect to it, today we are going to conclude. If you have any doubts, Sarthak, please go ahead, then we'll discuss into, if I cannot answer today, you can discuss in later session. Okay. Okay, thank you, Sarthak. Thank you for joining.